Okay, here's a little video to help support this idea of voltage and electric potential. So electric potential is another way of saying voltage. So I'm going to start with this idea that maybe there could be some charge in space, say 5 microcoulombs, or at some point x in space, and maybe it's some distance r away. And we know that the electric field strength at that point, first of all, the electric field, because this is a positive, would be pointing away. The electric field strength at that point is K Q divided by R squared, where this Q is the 5 microcoulombs. Likewise, if same situation, if you have 5 microcoulombs, some point x in space, distance r away, and let's suppose there's another charge here. So instead of being to some point in space, we have 2 microcoulomb charge there. We know that because there's two charges, we have an interaction, we have a potential energy, and that's equal to K Q over R. And I'm just putting big Q, little q, just to say that they're two different charges. It doesn't matter. You could also go Q1, Q2. Whether it's a capital or not, it's not important. So we know about, or hopefully you guys know about electric fields. So electric fields surround a charge. And we know that when you have two electric charges, we have a potential energy between them. They're interacting. So then from one of the kind of notes, or the in the Moodle, we have this idea that voltage is electric potential energy per unit charge. So in that case, if what this is saying, like let's even put some numbers in here. Let's call this R equals, say, 10 centimeters. So EP equals 9 times 10 to the 9, 5 times 10 to the negative 6, 2 times 10 to the negative 6, 0.10. So let's see what that is. Hopefully it's a reasonable number to work with. Yeah, it looks pretty. Okay, it's at 0.9 joules. So that means that at this particular point in space, for every 2 microcoulombs you have there, you'll have a potential energy of 0.9 joules. So for every 2 microcoulombs here, you get 0.9 joules of energy. So for instance, if I change this to 5 microcoulombs, 2 microcoulombs, oops, if I change that to 4, same R, this would be 1.8 joules. So once again, for every, what this number is saying here is for every 2 microcoulombs, we get 0.9 joules. Okay, so then what voltage is saying, well, we're not interested in knowing how much energy there is per 2 microcoulombs. We just want to know what it is per coulomb. So to get that, you have to divide by the 2 microcoulomb. And then we get a unit quantity. And that is what we call voltage. That'd be, whoosh, it's a big number. 10 to the 5 volts. And I'll do one more just to really hammer that idea home. Okay, I have 1 microcoulomb. Over here I have 6 microcoulombs. They are a distance of, say, 1.2 meters away. The potential energy between those two charges is K Q over R. So that's 9 times 10 to the power 9, 1 times 10 to the negative 6, 6 times 10 to the negative 6, divided by 1.2. 99. That's 6e to the negative 12. 2. That's 4.5 times negative 2. Okay. So when I have this situation, at this point in space, for every 6 microcoulombs, I get 4.5 times 10 to the negative 2 joules. Now what I want to know, so that's for every 6 microcoulombs at that yellow circle. Question is, how much for every 1 microcoulomb? Or for every coulomb, I should say. For every coulomb. So to do that, we take, it's just a unit rate, so I'm going to go 4.5 times 10 to the negative 2 divided by 6 times 10 to the negative 6. And I get 7.5 times 10 to the positive 3, right? Yeah. That's volts. This is voltage. V is equal to EP divided by the charge. Okay, I'm just going to do a couple questions here, then we'll just wrap this up. What is the electric field strength at position X, which is 0.75 centimeters, or 75 centimeters from a positive 3 microcoulomb charge? Well, E is KQ over R squared. That's 9 times 10 to the negative, positive 9. 3 times 10 to the negative 6 divided by 0. I have to change that to meters. I get E is equal to 99, 3 negative 6, 0.75 squared, 4.8 times 10 to the 4 newtons per coulomb. So that's like 3. And that'd be pointing away. The field would be pointing away because the charge is positive. And then what is electric potential at that position? V equals KQ over R. 9 times 10 to the 9. 3 times 10 to the negative 6. 0.75. So I can calculate this all over again. I could actually just multiply it by the 0.75, but I'll start from scratch. 99, 3 to the negative 6, 0.75, 3.6 times 10 to the 4 volt. And then the last question is, if you put a 2 microcoulomb charge at that position, what would the potential energy be? And to do that, I'm just going to make use of this equation. EP is equal to V times Q. 3.6 times 10 to the 4. And we're working with the idea that we are putting the 2 microcoulomb charge there. Yeah. 0.072 joules. Okay, having said all that, you're not going to be asked a lot of questions on this, but some of the stuff does come up in one of the projects, so I wanted to go over it. But you don't have to do a whole bunch of practice questions on this. You'll be doing a bit, but not a ton. All right, thanks.